Hi everyone, welcome to our live stream about the Delta-T facts and fictions. My name is Klara and I'll be a host today. And we are so excited that you decided to, join us today. I'm tuning in from Slovenia, but with me it's Stanley, coming from Netherlands. But I know you're joining us from all over the globe. So just to warm us up a little bit, just tell us who you are, where you're coming from. We would love to hear how far this live stream is reaching. So just post in the chat. It would be very interesting to us to hear. Yeah, just to let you know, we are broadcasting today on the three different channels. So we are on the YouTube, LinkedIn, and on Facebook. But for whoever is not able to join the live session, just please share the link. The recording will be available after we finish. Today, we are going to discuss together with Stanley the increased trend of measuring delta-T. Hopefully, we will inform you a little bit more about how monitoring delta-T can help optimize hydronic HVAC systems, but also what are the limitations of it, right? So we want to emphasize that today, basically, it's all about you. We have a presentation ready, and Stanley can talk for days about it, but the best would be to just have a conversation, right? So if you have comments, questions, please post them in the chat box. We will try to answer them. By we, I mean Stanley, who's the expert on the topic. Shortly about myself, as I said, my name is Klara. I've been working in Danfoss for the last about 9 years, mostly coming from the product portfolio management. And today I will be a moderator, so I will try to pose all the questions that you have, all the comments that you have, give them to Stanley to be able to answer, and hopefully you will learn something more that you don't already know. Stanley, short info about yourself.
Yeah, hi, thanks, Klara. I'm Stanley. I'm from the Netherlands, as was mentioned, and I've been working in this field for 25 years. That's how I get all the gray hairs. And I guess that today is already well placed around the globe, because I saw Tunisia, Dominican Republic, Dubai, India is joining Egypt. So we're streaming live to a quite large audience. India again. Hi, Mohammed. And so yeah, we hope to have a good session today. And feel free to ask questions in the chat. We will try to answer as much as we can.
Great. So just to warm us up a little bit, Stanley has prepared the intro presentation, but then we are hoping to get as many questions as possible from your side. But Stanley, yeah, just start.
Yeah. So like I said, I have prepared a few slides, but maybe we will not get through them, and that's fine if you have many questions. But let's start. So I think this slide is now more or less a mainstay of all presentations I'm doing at the moment. Is that obviously it's no longer a secret that the Earth is warming up, and that and that we are changing the climate by producing too many greenhouse gases. And what maybe not so well known is that buildings, so the buildings that we all reside in and that we work in, that we live in, they actually produce quite a lot of these greenhouse gases. So in total, it's about 40%, of which 11% during construction. So there's also definitely something to be gained there by having, I don't know, lower emission shovels, or just producing less energy during construction. But 28% of the buildings of the greenhouse gases is produced just by heating and cooling the buildings. So and obviously there's something we can do. We can make nice new buildings that have LEED ratings or BREEAM ratings, and that are very energy efficient. And for sure we should do that, but also we maybe should look at our existing stock. So where can we save energy on current buildings, and how can we make them more efficient, and how can we work on that?
We have a first question. It's how can delta-T help us to reduce the greenhouse gases?
Right. So that's already quite, let's say, fast. I think because we will talk a lot about how this will help, I think that one of the things that we will see is that it will maintain the peak performance of our buildings. So how can we, so we can see first of all where the energy is going in the building, and then also we can or we can actually see where problems are arising. So where is overdue maintenance, because a building is has a certain energy efficiency when it's just built and when everything is commissioned perfectly. But obviously during use we will have wear and tear. We have all kinds of dirt getting in the system, and we need to be able to maintain that peak perfection, optimized working situation, and this is where delta-T can help. So as I was also saying, we are talking about let's say new buildings, which is I guess great, and you see a lot of adaptation of existing of new buildings that get more advanced, high LEED ratings. They are designed very energy efficiently, and that's also what you see. Companies are now putting more a higher price on buildings that are actually energy efficient, because also, I mean, if you're a bank or any other company, you want to have to show also your customers that you are being socially responsible and have a green building. So, and one of the things that can help with that is building management systems, or building automation and control systems. They tended to be mostly used actually for controlling the building. Temperatures were going in, and they were trying to use the BMS to actually control the indoor temperature, or indoor air quality, as we can say. But it can also be used for more, and this is also what you now see. It's like a trend where we are monitoring more data about the building, and where we are also using more of the data to act. But we also should say that data is not a solution in itself, right? It's not the question that, or let's say the idea that we now have more data automatically makes the building more efficient. You have to do something with the data, and one of the good parts is that we can always create more data about the building, because we can always say, okay, this building doesn't have a BMS, or a very rudimentary BMS, but adding additional sensors and additional cabling is not the most expensive thing to do. So we can optimize many of the buildings. And then if we're talking about optimizing, then delta-T is basically one of the key parameters to watch, and it's not always I would say watched that closely in many situations. So let's first talk about what it is. So usually when we're talking about delta-T, we are talking about the difference in temperature going into the equipment versus what's coming out. And it can be both a terminal unit, so I don't know, a Venco unit or a radiator, or a chiller or a boiler. And in both cases we talk about delta-T, and we use this actually also to design systems. And on the right you can see a slightly, let's say, a simplified version of how you can use this to calculate. And because basically there's let's say a part in there that's about the specific heat capacity of the material you're using, and in this case usually we use water. So and what you see is that we calculate the flow by taking the power that we want to put in the room and dividing it by the delta-T. And this is how, if we're talking about designing the system and designing the connections to the system, is how we basically know how much flow a certain terminal unit needs or a certain air handling unit needs, and also what kind of a capacity we need when we're talking about sizing the chiller or something. So, so it's really very much about how you design the system, and it's part of the job of the designer actually to make sure that also the system has the right delta-T from the beginning.
Stanley?
Yes, I hear you.
You hear me? Okay, good. We have a question about what is the recommended delta-T for a chilled water system?
Mm-hmm. Yeah, it's too general a question. I could say to answer. I mean, first of all, it's a design choice, right? I mean, the designer has certain choices that he can do. I mean, what is very common is to use 612. I think I didn't saw too many guys from US logging in, so I will just use metric for now. So it's 6 degree going into this installation and 12 coming back, so delta-T of 6. 7.5 is also common, but what you also see now a lot in West Europe specifically is we are using for cooling systems quite high temperatures. Let's say in combination also with radiant panels, so where it might be 14 going in and 18 going out, and then the heating would be also maybe 25 going in and 21 coming out, or maybe a bit higher even. But this also has a reason, is that many of the installations are using heat pumps right now, and that's also a very common, or let's say that's also one of the things that we will see more in the future, that heat pumps will be used more and more. And heat pumps actually function better under somewhat higher temperatures for cooling and lower temperatures for heating. So they basically are more efficient in this temperature. So this is why, first of all, radiant panels are a very comfortable system, but also the temperatures match really well to where your equipment, your generation equipment, is most optimally functioning.
Okay, Stanley, then we have a question from Mohammed. It's how does delta-T affect system retardation?
To be honest, I don't really understand the question. I don't know what retardation is. Maybe if Mohammed can maybe clarify what he means with retardation. I mean, let's say if you mean, I mean, retard is delay, I guess. So I mean, if you mean how it affects the speed of the installation, so how fast it reacts to changes, I think it's basically that is not really a factor, because if you look at the amount of energy that's put in the room is basically the same. It's just you use a different delta-T. So either higher or lower, and that means that you have to change the flow, as you can see from the formula, is that you need to use a bit more water if you have a smaller delta-T. I hope that was an answer, and maybe if he needs some more clarification, then he can come back with.
Yeah, just Mohammed, let us know if we haven't really answered the question, right? So just hopefully we got it right, but if not, then just ask a follow-up question in the chat. Okay, Stan.
All right. So as you can see, also from the formula, right? The delta-T is basically also a part of how much energy you actually transfer to the room. So if you change the delta-T and you keep the flow the same, then if you see from the formula that basically the amount of power you're putting into the room is also changing. And here it's also good to notice that a high delta-T is actually not a problem. So a high delta-T is always actually better for most applications. I would say all, because the generators function a bit more efficient. So if we're talking about boilers, for example, I mean, it's condensing boilers operate much more efficient with lower return temperatures because they are starting to go in condensing mode, right? Also, chillers are using less energy to cool, because if they have a higher, and that has to do with the chiller lift, which is a pretty big subject in itself, and a bit too much to go into, but chillers tend to also be a lot more efficient, or at least more efficient when they have a higher delta-T. And what is also important, if we have a higher delta-T with the same and we need the same amount of power, then we can actually reduce the flow. And the flow is directly connected to your pumping energy, which is pretty a pretty big chunk actually of the installation. I mean, if you look at a building, then you think, okay, the boiler is using a lot of energy, and you know, the chiller is using a lot of energy, but the pump is, you know, only it's not so big, and it's not using, I mean, generally speaking, we can say that 26% of your energy in the whole building goes to basically buildings. To basically the HVAC system of the buildings. So if we have a too low delta-T, that means we basically are wasting pumping energy that we could have used in a different way, and we can also have the lower efficiency of your boilers and chillers and all those things. And I mean, I think that most people, I saw a lot of people logging in from warm countries where they have mostly cooling. I mean, I think every engineer that works in this field has heard of low delta-T syndrome, where, you know, the system is just not functioning optimally and having a very bad functioning. That means it switches on and off a lot. I mean, also if you have a chiller cascade with the swing chiller, the chillers keep switching on and off, and specifically switching of chillers is quite expensive energy wise, and also if the chiller is running itself on a low delta-T, it's also very inefficient.
Stanley, we actually have a question from Ibnu on this topic, which is the best for chiller systems, high delta-T or low delta-T?
Yeah, high is always better in this case. So, and a low delta-T, we will also talk a bit about how that works, but later. But you know, like I said, if you have a low delta-T, your chiller is just a bit less efficient. It's also becoming much more sensitive to small changes in the load, and that means that again there will be a lot of switching on and off, which we definitely do not want. So generally, if we, let's say, design the system for 6K, so 6 degrees delta-T or maybe 7, then you should see that as the minimum. So it should definitely not be lower. And I mean, it's also if people are in maintenance here, for example, or if they are or if they visit existing buildings, specifically, just go to the technical room and look what the delta-T is in systems. And all the buildings, generally, it's not that good. So it's already there. You're losing a lot of energy, and it's quite easy to fix many of these problems. I mean, proper balance in the system is one of the things. So make sure that the right amount of water is going to the right place. But that's already, you know, if your delta-T in the building is not great, then basically already, you know, you're wasting energy.
Okay, and then we have a follow-up question: is why are heating cooling generators more efficient with bigger delta-T?
Yeah, this so for boilers, basically one of the things is that the return temperature has to be below a certain temperature, more or less. It depends a bit, but I thought it's like 50 degrees. To start in condensing mode, where they basically retrieve like 10% or 15% of the energy from condensing function. So that's one of the things. It's also and for chillers, it's about the chiller lift basically. So I don't have any slides prepared on it, so maybe we can discuss this also later. But it's the difference in temperature between the condenser and the actual chiller. So where so the condenser and the evaporator. So where the cooling happens and where the additional energy is actually let's say put to the outside air. I mean, through a cooling tower or a condenser or something. And the chiller lift is influenced by the average temperature. So let's say the average delta-T between your supply and return. And if the chiller lift becomes higher, which means that your return temperature will also be lower if we're talking chillers, right? Because the chiller is usually set to control a certain supply temperature. I don't know. Let's say if you designed 6 degrees, it will be 6 degrees. So if your delta-T is not correct, it means you will get too cold water back. So instead of 12, you maybe get 8 or you get 9. So again, first of all, you're wasting water or wasting energy on pumping water that is basically unnecessarily pumped, because you could have done it with half the water more or less. But also the chiller lift changes, and that makes it less efficient. I hope that's quite.
I think it answers the question quite good, Stanley. Thanks. And then we have another question from Andre. It's which country actually needs high delta-T?
Yeah, I guess we can. Country is maybe a bit too specific. We can say maybe climate regions or something. I mean, high delta-T anyway. Again, it's always good if you can get it done. But what you see is specifically in moderate climates, like I'm here in Netherlands, where we have, like, I mean, it's in summer it will maybe get sometimes 30, but not higher. And we also have cool seasons, like changing seasons, like autumn and spring, where maybe sometimes we're cooling, sometimes we're heating, and then we have winter where we're heating. But those can be used quite well for, I would say, systems that have a high temperature level, where the delta-T is maybe not as big, but where we have higher temperature levels, like I was discussing, like radiant panels, and that use quite high temperatures for cooling and quite low temperatures for heating. However, specifically for radiant panels, the limitation is always the size of your room, right? Because you have only so much ceiling as your room is big. So the how we say the capacity you have on radiant panels is quite limited. Because also you cannot make the temperature in the ceiling too low, because then you will have condensation and it will start to rain inside. And I don't think many people would like to have their own tropical rainforest in the office. So I guess that's not really wanted. So I mean, as far as which country, high delta-T, again, always good if you can arrange it. However, if you have a high load on your system, I mean, Malaysia, for example, which I know quite well firsthand, they have usually more or less similar weather. It's always quite warm there. So there you are always running on more or less design conditions or close to. What we will see later is that if you can run on partial loads, then your delta-T can go up quite a lot. And that is so basically where you have, let's say, intermediate seasons and where there's a difference quite a lot in conditions. There you can have high delta-Ts during normal running operation.
Stanley, actually, we have a comment, not that much of a question, but maybe you can comment on a comment from coming from Milind. He's saying that high or low delta-T is actually a subjective question, as this depends how the system is designed and accordingly how chillers or heat exchangers are designed. So basically, no definite answer is possible without knowing the application.
That is very true. I was trying to kind of talk around this one, but yeah, that is true. I mean, but let's for this particular purpose say that low delta-T, if I'm talking low delta-T, it's lower than design conditions, and high delta-T is higher than design conditions. So that is basically where we say high or low. So because I mean, for a heating system, 20 can be good. For a cooling system, generally speaking, it's quite high. But also, if you're in heating systems for floor heating, for example, 20 would be very high again. So it's correct. It depends a lot on the application, on the system. But again, if I'm talking high or low, I'm talking here versus design conditions. So if the design condition would be 6, then a low delta-T would be 4, and a high one would be 10.
Okay. And then we have a question coming from Johnson. It's what is the effect of ambient temperature on delta-T?
In essence, I mean, if we're talking about ambient temperature outside the building, I guess it has to do with your system load, essentially. So if we're talking a high load, so generally speaking, your system is designed for a certain condition, right? So you say at 30 degrees ambient temperature or outside temperature, I want to be able to get 22 degrees in the room. That is then how you design the system. And then also, if you use the formula, then basically you can calculate how much energy you lose through the walls, and then you can basically calculate how much power you need to get there, and then from there follows your delta-T and your flows. So, but as I was saying, also in the Netherlands, for example, generally speaking, or most of West Europe and also the US, we have intermediate seasons where you never actually really have these conditions. So you basically I mean, in the Netherlands, you may be sized for -10 or -15, and for +30 or +35, depending on how. But generally, those conditions actually, I mean, I can't even remember when it was -15 here. It was the last time we had the 11 cities tour. So that's at least 20 years ago, I guess. So, and that means that at that point, when your outside conditions are different from your actual design conditions, you're going to run in partial load. And if you run in partial load, then you can have high delta-T, which again is then higher as designed. Maybe I can just quickly. Oh wait, just here. So just to talk about that, if we see the graph here, it's about a typical heat exchanger curve. So basically, from here to here, this is how much flow goes through the heat exchanger, and this is how much capacity we actually produce. So I don't know if this is 2.5 kilowatts. That means that at 100% of the flow, you have 2.5 kilowatts output here. However, you can see that at 50% of the, so at 1.25 kilowatts, you actually need only 20% of the flow. That is because there is much more energy transfer in your heat exchanger than if the flow is higher. And you can also see that if your flow actually increases even more, you hardly get any additional capacity out of it. But we do see a very big reduction in the delta-T. So and this is actually where we are talking again, high and low delta-T. This is a low delta-T because it was designed for 6 and now it's only, I don't know what, 3.3. And this is then high because it's actually 15. So and this is where we say, okay, if we are talking about having good delta-Ts in the system, we also have to look at what happens during partial load. And in partial load is where you can really make a difference. And in many countries, partial load is basically the de facto condition. I mean, even in, let's say I was talking Malaysia, where they have high loads, generally also there the system is oversized, because that's also one thing we do as designers, right? Is we put safety factors on safety factors on safety factors, and that's what's causing also sometimes that our system is just quite oversized.
Okay, Stanley, then we have a question coming from Alexei. It's more related to the topic you were discussing a little bit before about the specific country or country specific. And he's asking, isn't the allowed delta-T more dependent on the heat source type and less related to the specific country's locations?
Yeah, I mean, that is also what I alluded to earlier, is that you see that some of the many systems are now actually going towards heat pumps, which generally do not like, let's say, high temperatures. So this is also a problem that you see is with many of the radiator systems that are, have been built in the last, I don't know, 80 years. That heat pumps are not really playing that well with that kind of system, because maybe you need 90 degrees even if you have really old systems. Or 70 degrees supply temperature, and everything above, top of my head, 55 just reduces the efficiency of your heat pump quite a lot. So yeah, your delta-T is a design choice, and your design choice obviously is dependent on what you want to achieve with your building, and also what kind of equipment that you have available or that you want to use. If you want to use a heat pump, then yeah, you need to basically adjust your delta-T regime to your heat pump and make sure that at most times, as much as possible, you're operating in the most efficient zone.
Okay. And then we have a question or request if you can explain about delta-T on refrigerants and power savings.
Well, it's a bit outside my because if I hear refrigerants, I'm thinking, yeah, okay, we can say either it's let's say cooling equipment in supermarkets or something, which I kind of, there's another live stream for that, I would say, because that's outside of my expertise. If we're talking about let's say VRF systems that we have that also are quite widely used, I think basically the same logic applies. However, I would say I cannot really explain a lot about it. It's a bit outside of my zone, and I don't want to tell you anything that I'm not 100% sure of. So.
Okay, Stanley, but I think that's fair enough, right? We have quite a lot of questions popping up, so thank you for being so active. The next one is coming from Hussein. I'm sorry if I'm pronouncing your names wrong. I'm trying, but he's asking, does installing a PICV improve the delta-T?
Yes, and that's also, I would say, one of the reasons that you see that most of the buildings nowadays are using some kind of pressure independent technology, because as you can also see on the graph that we have now in front of us, if you have an overflow, then you're basically just wasting energy, and you're also reducing your delta T. So, the pressure-independent control valve will definitely reduce overflows. It will make sure that you have the right flow at all times, but also it will ensure that during partial load, and you can see here that the partial load is actually one of the most interesting conditions here, is that you will have the exact right flow there, and that also there is no influence from other valves in the system, because that is also, I mean, if you have a certain flow but somewhere else in the system a valve closes, then the flow through your valve may rise again and then reduce again your delta T. So for sure, PICV has a huge influence on delta T, and I would say that if you do nothing else on retrofitting your building, but just put delta T, let's say PICV in, already you will see a very big increase in the delta T.
Okay, and then coming a question, he's saying for air-cooled condensers, the delta T will be around 10 degrees for LT applications. I would say that means low temperature applications, and 15 degrees for MT, so medium temperature application. Is this recommendation good?
There, there I will also not state anything, because I'm an expert on the secondary part, right? So this is kind of like the primary side, where I would say that does have an impact, but it's also again related to the chiller lift, and also we should say that it's not necessarily something that we can really influence, because it's also heavily dependent on your ambient temperature, your outside temperature. So you can want it to be something else. However, it is up to nature to decide. And to be honest, like I said, it's more this, let's say, the primary side, which I know something about it, but I'm more an expert on the secondary side.
Okay. For now, I don't have any other questions in the topic. They will probably pop up, so maybe Stanley, you can just continue with the flow.
Yeah. So as I was saying, so the delta T is quite directly linked to how much energy you transfer, and also you should basically be aware that, and I think, I mean, we had some great questions actually that were asking me to explain this, is that it's very much into how you design the system, but also, again, if you design the system for 6, you should see this as a minimum, and you should definitely allow temperatures to go, the delta T to go higher if the system wants to. So
Stanley, sorry to interrupt you. There is another question, and it is, how much energy is the pump using, and do we care?
It's like you should care, basically, because generally speaking, it's maybe 20 to 30%. Generally, we can say more or less 25% of the energy that you put in heating or cooling the building goes to the pump, and our friends from Drives can tell you that by reducing the pump speed, actually also the amount of energy you get back is a factor, because of the affinity law, it's actually much more than what you reduce. So if you reduce the speed by 10%, or the pump head by 10%, you will get much more energy than 10% back. So yes, you should care about what your pump is doing. That is also why, for example, PICV is such a good idea, because it will minimize your flow and make sure that you minimize your pump head, and that is one of the easiest savings that you can do.
Okay, and then we have a question from Sojo. What are the influences of high differential pressure on a high-rise system to cause low delta-T syndrome? Is it also high design?
Yeah, the higher pressure, or I would say, so you have, if you have a higher building, then obviously the pressures in the system will be higher because you have the water column pushing onto it. Like 10 meters is like more or less roughly 1 bar. So does that have an effect on the delta-T? Not really, because essentially, specifically also if we're talking about pumping, because the same column that you have to push up is also pushing down on the other side. So essentially, there is not a lot of change in the differential pressure. So you can use, for example, the same pump head. And as far as delta-T, let's say the heat capacity of water doesn't change enough in this pressure to actually make change it for the real calculation. So no, it does. The high rise does not influence the delta-T as such, but it does affect your. But it does affect, let's say, the standards that your system must comply with. In other words, that if you have a high building, then you need to calculate higher static pressures in your system.
Okay, and then we have another question coming from Mohammed. I think it's a follow-up question. Is what is delta-T affected by?
Well, that almost like he saw my next slide, I guess. So first of all, actually, as we said, it is affected by the load in your system. So we can say the delta-T is at design conditions when you're running at full load. If you are over pumping, then you will have to low delta-T. And if you go to partial load, then you will see a higher delta-T, or should see. But what will cause a low delta-T? It's obviously, as we discussed before, bad hydronic balance, so overflow, over pumping. It's also very connected, this issue, because what is if the system is not balanced properly, so they don't use PICV, for example, then you will have some part of the system where there's not enough heating or cooling. Generally, the easiest way to solve that, at least to the contractor that has to solve this problem, is to just increase the pump head. That will then again create all kinds of other problems. But one of the things is it will basically destroy also your delta-T, because all the units will be overflowing. And in the end, obviously, when the control starts to operate, it's a bit less problematic. But for sure, this is not good. Other issues can be, dirty coils. So if you have scaling inside the coils, then your heat transfer is just reduced. So that means there is like basically an insulation between the water and the air that you're cooling or heating, and that will also destroy the energy transfer, and therefore also your delta-T. Filters can be, let's say, a problem, as we will see also next. And also, in some cases, if a valve is broken or an actuator is broken, I mean, it's certainly not let's say, unusual for maintenance guys to make a quick fix and for a broken actuator and just open the valve and then forget about it, because there's no, and then for sure you will have too high flows and also problems with the delta-T.
Okay, we have a question, Stanley, about what is the biggest misconception about the delta-T?
I think one I kind of encountered a few times is that it's bad actually if it is higher than design. which is actually completely the opposite. If that is the biggest, I wouldn't know. I think that it's a bit, also probably a bit regional questions. So in regional, some people might discuss it in different ways than others. But I think that generally higher delta-T is better. And so if you designed your system for 6 and it's 8, and I should note your indoor temperature is still okay, then it's not a problem if it's higher.
Okay. Then we have another question coming from Holmes Nababan, and it is, what kind of control is needed to get higher delta-T, and where is the optimal location for installing the differential pressure transmitter sensor for the pump unit to get higher delta-T, especially during partial load?
Wow, that's basically in one question a whole new presentation rolled there. Let's see if I can get let's say the main points. So let's say higher delta-T will, if the system is properly designed, will happen of its own when you go in partial load. I will, after this one, show you a bit about problems and also how to control. So I'm getting back to the first part of the question a bit later. And the pressure transmitter sensor, that's a very interesting topic, which I could probably talk for 2 hours about. There is a few ways to do it. I would say the very, very best way is to put the pressure sensor at the end of each branch. That will give you the best and lowest pump head that you can have at all times. If you want, but that obviously is also costly in some cases. It's wires and sensors and stuff, and also your BMS must be equipped for that. But if you want, let's say a shortcut, then generally you can say, or a generally accepted way is to put it in 2/3 of the installation. But then if you then ask me how to calculate 2/3 of the installation, I kind of don't know actually how to do that. I would say if you put the sensor too far away, so if you use only one sensor, if you put it too far away, you will have problems with underflows in partial load because then certain rises will not get enough pump head. If you put it too close, you will save less energy. So, it's not such an easy question to discuss without an actual installation where you can actually, pinpoint something. But again, if you want to be safe, end of each rise or each branch will give you the best results and the lowest pump head and the best savings then in this case.
Okay. Thanks, Stanley. For now, we don't have any additional questions, so I think we can move on with the presentation, and then let's see what else pops in.
Yeah, because I kind of forgot who asked the question, the long one. Holmes. He asked about how can you control high delta-Ts. So what we try to do here actually is we have a climate chamber in Slovenia University where we can do testing, and we try to simulate, in this case, a problem. And the problem here is the clogged filter. So we have a Venco unit, and as you all know, most Venco units have or I think most of you would know, have a supply of fresh air, but also they recirculate some of the air from the room, either from above the ceiling or from some grid somewhere. And usually that air is filtered separately, and this filter obviously can get dirty. And then what you will see is that the Venco will have a lower flow of air over the coil, which then will impact actually the delta T, because the characteristic of the coil will change a bit. It's, by the way, not dissimilar to having a lower setting in the fan coil. So now what you see is in the red section here is where we clogged up the coil, and I think it's also important to notice here that that we should that this now wasn't let's say a sudden event, but generally speaking, this will take months or maybe even years to happen. And what you see here is your delta T is dropping. So here it was like 8, and it's going to 3.8 maybe. But what's also important to realize is that this is not the only thing is happening. Your room temperature, which is this line, is going up. In other words, what is now happening is that you have a lower delta T, but you also have a higher room temperature. So so what you're now basically wasting, energy on two sides, and you don't even get the required indoor air quality that you needed. So so yeah, it is and this is where you have to realize that just controlling the low delta T is energy saving maybe, but it's also will just make your building worse. And in the end, I mean, also we are cooling and heating the buildings to create a nice indoor climate, right? And not to be more efficient, because otherwise we would just not put any cooling or heating in it at all, because that would be the most efficient. So what you then can see if you look at this graph, where we put actually some control on the delta T. So the here again, this is where we switched we changed the filter, or we blocked the filter. So here everything is okay, and then you see the delta T drop to, I don't know what, 6 degrees, which was the temperature that we wanted to control. And so we said, okay, delta T cannot go below 6 degrees, but and so what then will happen is then the valve will close a bit instead of opening further because the room temperature is not achieved. It will close a bit and try to maintain this delta T, and you can see that it's trying to control. But you also see here that the room temperature is also higher than required, because this is the set temperature that you need. Sorry, a blue line here, and the red one is the real temperature. So we have too high a temperature. So basically, if you're asking me how you reduce the delta T, is basically maintain your system and make sure that your filters are clean, your pipes are clean, your system is properly balanced, your pumps are on the right settings, and everything is working as it should be. Because as soon as you have if you have a delta T problem, that means something is wrong in your system, and that is also, as we can show here. And basically here, this orange line here is an alarm, basically, that we are generating our systems, where we say, okay, the delta T is now too low, and this is also what should happen. So you should monitor the delta T, and as soon as you have a problem that it is lower than what you think it should be, then an alarm should go, and somebody should basically fix that problem.
Okay, Stanley, just a question from the audience is, how can I control on delta T? Do you have thermostats with 2 sensors?
Yeah, we do actually have. So basically, it depends on how you want to do it. Like if you have room controllers, DDCs, for example, in your BMS, then you can attach 2 sensors to the DDC and control it in that way. However, we also supply actuators that are directly connected to the network, and that are on BACnet, and they can also have two sensors for supply and return temperature, and basically the actuator can then control that. So there, it depends a bit on what method you want to use, but in the end, if the delta-T needs to be adjusted, that always goes at the expense of your room temperature, and that means that you are closing the valve while actually the room needs a bit more energy. And you see that here, more or less, it is under control, or more or less it still works pretty well. But it could be in other situations that your room temperature will just go higher as long as your delta-T is not maintained.
Okay, and then it's a follow-up question is, why can delta-T control not be okay?
Yeah, I think, one of the things, again, I've seen is that some people let's say, limit the upside, which is definitely not something to do. And again, it should not be used for a long time, because the delta-T gives you an indication that something's wrong. So more or less, you can use to control the delta-T, and basically also in some cases you have to. I saw guys logging in from Dubai, for example. Dubai has a lot of district cooling systems, and if your delta-T on the building is not correct, they will just give you a nice penalty on your energy bill, because they also know that if they have to pump too much water, and if also the delta-T in their system is not good, they're running on very low efficiency, and they're making you pay for it instead of paying it themselves, which is, I would say, quite reasonable. So in certain cases you have to, and also district energy systems, district heating systems, district cooling, they want you to supply high delta-Ts, or at least design delta-Ts and not lower, because it wreaks havoc on the efficiency of their own system. And you can control it, the delta-T, but it should be a temporary thing. So more or less, you should have an alarm, and okay, delta-T is not correct, I need to fix something. It's not something that you can control away, because if you control it away, basically you're either destroying energy or your indoor temperature is not correct.
Okay, and then it's a question, what should be looked at in case delta-T is higher or lower than expected?
Yeah, again, as higher is not a problem, and lower was, the filters, and more or less you can kind of see, in the situation where it is that maybe you can say, okay, this is like an air handling unit that is on the high capacity, but I just don't seem to be able to heat the water to the right level. Then maybe it's the problem with the coil that is fouled or something. But yeah, usually it's a problem. So yeah, sorry.
Yeah, sorry, I was muted. But our hour has actually ended. So I think we are ready, since we don't have any more questions, just to wrap up, and just if you can just conclude on the whole presentation, right? And then I think we can wrap up for today.
All right. So it was a lively session today, so that's good. It seems that we found an interesting topic. I will just wrap up in like a few more minutes. So one of the things also the delta-T will give you basically is if you combine it with the flow, which can be either a flow indication or actually measured flow, then you can also measure how much energy goes in and out. Remember the formula, which can be used to also determine, like, okay, where are energy hotspots? So if I have two offices that are of the same size, same orientation, then what is then why is one using twice as much energy? So that's also something definitely to think of when you're anyway have this available, is delta-T, because you want to optimize your system. So then you can also see where is too much energy is used in the building. And then just to conclude, as we said, we need to be more conservative with the energy we use in buildings. We can obviously make new buildings more energy efficient, but we can also make older buildings more efficient by being more aware of the state of the system that it's in, and this can be done with data that comes from BMS systems or BAC systems. But again, I mean, you need to understand what you need to do with the data, and I try to explain to you in this presentation what to do with the delta-T measurements that are also coming up and also used quite a lot, but not always are they used in the right way. And I think that's a wrap, more or less.
Good, thank you, Stanley. Then I think we can wrap up for today. So I would like to just thank everybody for joining and really being, posting questions, commenting, being engaged into the topic. And of course, thank you to you, Stanley, for sharing your expertise and knowledge. I believe we all learned something today. And yeah, have a good day.
Yeah, and maybe I don't know. Maybe if there's some questions still open, we will try to see if we can do something in chat, or we can come back late. We will come back later, so we'll definitely scan and see if there's more questions that need answering. So thanks for tuning in. Also, thanks, Klara, for being such a gracious host. So
thank you. Okay, bye everybody.
Bye.